All right, so today we're talking about slope fields. And to talk about slope fields, we kind of go back in time, back earlier into first semester when we talked about solving differential equations to start with. And this was actually one that we started off with in our notes. This is the very first one we talked about, was dy dx equals 2x. So this is telling us that the change in y over change in x at any point on some graph is 2x. All right, so the slope at any point is 2x. We can find an original equation of this. Well, not just one original equation, but we can find infinitely many possibilities by doing the antiderivative. And let's take a look at that first before we actually look at the slope field. So to solve this differential equation means to find the original equation, solve it for y. And the first step in doing that, we're going to multiply both sides by dx to get the dy on one side and the dx over on the other side. And our goal then is to have all the x's on the dx side and any y's on the dy side. So we don't have any y's. We're kind of set up. We're good as it is. We can take the antiderivative of both sides. And what's the antiderivative of dy? Y, as I just gave it away. And antiderivative of 2x, x squared plus c. And so we talked about how there's lots of different equations that have a derivative of 2x. Y equals x squared, y equals x squared plus 2, y equals x squared minus 7. We can go on for days naming different functions that have this as a derivative. And then we learned that if we had a point on the original graph, then we can find out the exact equation. But if we don't have a point, then there's lots and lots of different possibilities. Well, basically what a slope field does is give you a graphical representation of those possibilities. What we're going to do is figure out the slopes of a number of different points on our original graph and draw little slopes, just little tangent lines basically. And when we have all of those together, we can visually get an idea of what the original graph could look like. Again, there's lots of different possibilities, but we get an idea of the flow of the graph and what it should look like. So let's go ahead and take a look at this. You have some AP questions like this. We'll look at some next week that are a little bit more, that are actual AP questions, former AP questions. This one is not, but it's similar. On an AP question, you probably wouldn't have to fill out this many slopes, but you'll see filling out the slopes is not too tough. Our slope here is 2x. Right? dy dx is going to be 2 times x. So if we look at this first set right here, all of these have an x value of negative 3. What's our slope going to be for all of those? Negative 6. Then all of these x values are negative 2, so 2 times negative 2, we're going to have a slope of negative 4. X is negative 1, so our slope here is negative 2. And here, x is 0, slope is going to be 0. 2, 4, and 6. All right, so we've got all of these slopes now. We just want to represent them graphically below on the slope field. So I'm going to start with the easiest ones. Whenever x is 0, the slope is 0. So if we look down at our graph, when x is 0, that would be right here on the y-axis. Each one of these has a slope of 0. So I'm going to draw just a little line with a slope of 0. Then I'm going to look at the x equals 1s, all those points. When x is 1, the slope is always 2. So for all of these points right here, the slope is going to be 2. So all I'm going to do is go from this point, go up 2 over 1. And then I'm also from that point going to go down 2 to the left 1. And there's our little slope. Up 2 over 1, down 2 over 1. Now, on the other side, when x is negative 1, the slope was negative 2. So we're going to go down 2 over 1, up 2, left 1. So pretty similar over here, just flipped around. When x is positive 2, the slope is 4 for all of these points. Well, I don't want to go up 4 over 1 and then down 4 over 1, because then we're going to start getting slopes a little bit different sizes. You can, it's not a big deal. But what I'm going to do to take care of that, I'm just going to go up 2 over 1/2. Right, up 2 over 1/2, that's still a slope of 4. 2 divided by 1/2 is 4. But that way, they are kind of similar in size. Not a big deal, but up 2 over 1/2 for each one of these. And then at negative 2, when x is negative 2, slope is negative 4. So we're going to do down 2, left 1/2. Or sorry, down 2, right 1/2. And then up 2, left 1/2. And then last but not least, the 3 and negative 3, those have a slope of 6 and negative 6. So over here, I'm going to go kind of similar to the last one. I'm just going to go up 3 over 1/2 instead of up 6 over 1. Down 3 over 1/2. And then just negative on the other side, so we're going the other direction. It's like going back to kindergarten and connecting the dots. Alright, so we should get a slope field that looks kind of like this. Now, we kind of cheated. We did some stuff ahead of time. We figured out what the original equation could be, like the possibilities, y equals x squared plus c. Right, so we know that the original equation should be a parabola, and then its vertex should be on the y-axis somewhere, right? It's just being added or subtracted, so it's just shifting up or down from the origin. And if you look at the slope field, you can kind of see the shape of that. What I compare like a slope field to is kind of like the current in a body of water or a river or something like that. Let's say we dropped like a leaf in the water right here. These little slopes kind of tell us the direction where it's going to be flowing and moving. So let's say it was right here. Well, the slopes are kind of pointing down, and then they start to shallow out a little bit. Then we have this horizontal slope, pushes it this way, and then the flow over here is pushing it up that way. All right, so we can kind of see that parabola shape. No matter where we put it, it's going to have kind of that same flow in this case. Sometimes it's going to look a little bit different. But here we know that that equation is going to be some parabola with a vertex on the y-axis. All right, last part here. We've kind of done a little bit of this on our own already earlier on. It says to find the particular solution, y equals f of x. So it means like find the original equation, solve for y with this initial condition. So now when we have that initial condition, we can figure out what c is. So I'm going to go ahead and steal some of our work from up here. You might want to just draw an arrow, or you can copy it down again if you want. Oops. Right, so we started off dy dx equals 2x. Remember, we multiplied both sides by dx to get to this position. Took the antiderivative, and this is what we got. But now we want to know what's the actual equation. We can figure that out by substituting our values in. We know that x is 0 and y is -1. So c ends up being -1. So our particular equation here would be y equals x squared minus 1.